In today's video, we'll take a look at Bitwise operators. So what are they and how do they work? Well, first things first, Bitwise operators are just like any other operators, like addition and subtractions. Basically, they take in one or two operands, and using those, they spit out a result value. So let's start by declaring a simple variable r, and that will hold the result. I'm going to also print it on the screen. So I'm going to say here result and %d \n, right? And then that's r. Now the first operator we're going to look at is the AND operator. The AND operator is just 1 ampersand, right? So just 1 ampersand, not the logical AND operator, which is the 2 ampersands that you might have used in the past. Right? So if I say here r equals 1 ampersand 1, what should the result be? This is not an addition, so we're not going to get 2, for example. So if I try to run this, you'll notice I get the result 1. So 1 and 1 is 1. Let's take a look at the rules behind the AND bitwise operator. Now, the bitwise operators work at the level of, as the name implies, bits, right? So we're just going to take a look at the bits, so either 0 and 1. Therefore, there can only be 4 combinations of 0 and 1 digits, right? It can be 0 and 0, 0 and 1, 1 and 0, and 1 and 1. What we have done there was say 1 and 1, and what we got was 1. So that was to be expected. That's how the AND operator works. Okay, so if I change this to, for example, if I change this to be a 0, I should get 0, right? That makes sense. I got 0. Okay, nice. Now that's fine, but what if I try to work with numbers higher than 1? So if I say, for example, 1 and 2, what do I get? Well, if I try to run this, I'm going to get 0. But why is that? Well, that's very simple. Since the operators work at the level of bits, we first have to think about not the numbers 2 and 1, but the base 2 representation of those numbers. Now, I really suggest before diving into these operations that you start learning about converting between base 2, base 16, and base 10. I do have a course on Skillshare that you can check up top or in the description below. All right, so we have to think about the numbers in base 2, right? 1 in base 2 is just 1. That's simple. But 2 in base 2 is definitely not 2 because we don't have the digit 2. 2 in base 2 is actually 1, 0, right? So now, if we think about how they are represented, we have 1 here up top, and then we have 1, 0 here. And if we align them properly, like so, the AND bitwise operator all it does is look at each column, and using those just 4 rules, it gives us an end result for every single column. So here we have, for example, 1 and 0. Well, 1 and 0 should give us, as a result, 0. If we take a look at the page here, 1 and 0 is 0. That's nice. But then what? Here we don't have anything. Well, if we don't have anything, we just say 0 here. Okay, so now we have 0 and 1. And if we take a look at the page here, 0 and 1 is actually 0. So we can just say 0. And well, since 0, 0 in base 2 is actually just 0 in base 10 or in any other base, if we run this, we're going to get 0 as a result. So let's try, for example, here 9 and 5. So if I say 9 and bitwise and 5, what should we expect as a result? Well, let's think a bit about it. We have to convert every single number to binary first. So 9 in binary is, well, that should start with a 1 for the 8, and then we have 0 fourths, 0 twos, and a 1 at the end. Right, so that should be 2 to the power of 0 plus 2 to the power of 3. Nice. And then we have 5. 5 is, well, we start with a 1, that should be 2 to the power of 2, no 2's and a 1 at the end. So that should be 2 to the power of 0 plus 2 to the power of 2. And we align them to the right. And let's calculate the result here. So first, 1 and 1 is, let's take a look at the page here. 1 and 1 is, what do you know, is 1. So this is the only case where we get a 1 for an bitwise AND, right? If it's any other case here, the result is actually 0. All right, so this should be a 1. 0 and 0 should be a 0. 0 and 1 should be a 0, cannot be 1. And 1 and 0 should also be 0. And this is the binary representation of the result. The actual number, well, that's still 1. Right, so if I try to run this, I'm going to actually get 1 as a result. Now, all the other bitwise operators work the same for the most part. So if we take a look at the OR bitwise operator, which is down here, you're going to see that, well, in this case, we still have all those 4 combinations because, well, we have 2 bits that can be either 0 or 1, but the results are kind of flipped, right? So we get 1 in most cases, but we get a 0 when both of them are 0. So then let's try to actually figure out the result of 9 bitwise OR 5. So the representations are like so that those don't change. It's just the rules based on how we get the result. So here, 1 or 1 is, well, that's 1, right? If we take a look at the page here, we see 1 or 1 equals 1. Fair enough. 0 or 0 is actually 0. This is the only case where in bitwise OR operations we get a 0. 0 or 1 is a 1, and 1 or 0 is also a 1. So we get this number in binary as a result. But what's that number in decimal? Well, if we try to run this, that is 13. Right, so that's because we got here a 1 plus a 4 plus an 8. 1 plus 4 plus 8 is actually 13. Now there's a variant to the bitwise OR operator, which is the exclusive OR, which is noted like this. And the exclusive OR is very, very, very similar. Right, if you take a look at the page here, this is the bitwise OR, and the exclusive OR is very similar except for this last part, where it says if you have both inputs be 1, both bits be 1, you should get a 0 as a result. Right, before it was if you have both bits 1, you get a 1 as a result. So that's the only difference. So let's try to predict the result of this. Again, 1 and 1 is going to give us 0, as I said before. 0 and 0 is going to still give us 0 as like with the bitwise OR operator. 0 and 1 I'm going to get 1, and 1 and 0 I'm going to get also 1. So the result should be what? Should be 1, 1, 0, 0 in binary, which is 12. That's because we got here 2 to the power of 2, which is 4, plus 2 to the power of 3, which is 8. So 8 plus 4 is 12. Now there's one more operator that we haven't looked at, and this is the bitwise NOT operator. The bitwise NOT operator is denoted by this symbol, not by the exclamation mark, which is the logical NOT operator. This is the bitwise NOT operator, right? And this guy just takes in one input, one number, one variable. We can say here not, for example, not 5, right? And all this does is basically, if we take a look at the page, we also have it listed down below. All it does is flip the bits. So if it sees a 0 on a column, it just changes it to a 1 in the result. If it sees a 1, it changes it to a 0, and so on and so forth for every single bit. Now, 5 is what? 5 is 101, right? So let me actually change all this. This is 5 in binary. Fair enough. And what should be the result? Well, the end result should be, well, instead of 1, we put a 0. Instead of 0, we put a 1. And instead of 1, we put a 0. Right? That's the expected output. If I try to run this, I should get what? I should get 2. Because that's the binary representation for 2. But if I try to run it, you'll notice I get -6. Why is that? Well, it's going to be more obvious if instead I print it in hexadecimal. So if I say here %x instead of %d and run it, you'll notice that we get a lot of F's and an A at the end. What happened? Why didn't we get just 2 here? Well, notice when I said that a nothing means a 0, well, for not, a nothing here would actually be converted to a 1. And since an int has 4 bytes, that means it has 32 bits, it has 32 digits here, or it should have been padded up until we have 32 binary digits. So that should be 000 and a few more times, 1 2 1 2 1 2, this many zeros. So this is our actual number, therefore the result should be full of 1s, just like so. And well, if you convert each 4 binary digits to an F, you'll notice that we get the proper result here, right? Before, with the and or, we didn't get affected by this simply because 0 or 0 is still just 0, and 0 and bitwise and 0 is still just 0. So in either cases, we wouldn't get a different result. But in this case, 0 is actually turned into 1. And that's why we get a negative number. If we were to, for example, use an unsigned int, so if I say here unsigned int, and print this as an unsigned int, so %u, you'll notice I'm going to get a very, very big number. Simply because, well, we got a lot of 1s here, and that's to be expected. And that's really all there is to bitwise operators. So what they do is, as the name implies, just apply an operation for every single bit inside both or just that one value, right? So you have to think about the binary representation of each value and then do the operation one by one. The operations are very simple, as you notice, just 4 cases and 4 results, right? So just take a look at the table, or maybe even learn it. You can do so, it's very simple, and you're good to go. Just be careful with the size of the actual container. So where you're noting a really big variable here, like this one that has 32 bits, you're going to end up with a probably really big number or really small number, depending on what you're doing. And you're going to get 1s here. And really, that's about it. Thank you guys so much for watching. I hope this has helped you. If you do have any questions, do it in the down comments below or on our Discord server. Do check out the Skillshare course about hexadecimal and decimal and binary conversions, because this is going to help you in the long run when you're dealing with pointers and addresses and many, many other things. And it's also very short, it's less than 30 minutes. So give that a try. And you also get a 2-month free subscription to Skillshare if you use the link below. All right, take care, bye.